Welcome to this explainer. If you've ever stopped to look at a towering skyscraper, a massive jet engine, or honestly, even just the electrical wiring in your own house, and wondered why metals behave the way they do, well, you are in exactly the right place. Today, we're going to dive into the fascinating, totally microscopic world that gives metals their incredible macroscopic abilities. We're going to unpack the secret superpowers of the materials that literally built our modern world.
Let's start with a little everyday mystery, shall we? You drop a metal spoon into a hot cup of tea, and within seconds, the handle is burning your fingers. But if you use a wooden spoon instead, it stays completely cool to the touch. Why is that? The answer is completely invisible to the naked eye, hidden deep down within the atomic structure of the metal itself. By the end of this explainer, you're going to know exactly what's happening inside that spoon.
So here's our roadmap for cracking the case today. We'll start with the sea of electrons, explore heat and electrical conductors, move right along to bending without breaking, then mixing it up with alloys, and finally, a world of alloys. Let's get into it.
All right, Section 1, the sea of electrons. Let's take a look at the very foundation of metallic bonding.
Okay, the absolutely crucial thing to grasp right off the bat is this concept of delocalized electrons. Basically, when metal atoms bunch together to form a solid, the electrons from their outer shells actually detach. They don't belong to one specific individual atom anymore. Instead, they become delocalized, meaning they are totally free to roam and zip around throughout the entire structure. These wandering electrons, they're essentially the master key to unlocking how metals work.
Picture this, a massive grid of positive metal ions. Because they've ditched those outer negative electrons, the atoms themselves become positively charged. And they're just sitting there, suspended in what we call a sea of free-flowing, negative delocalized electrons. The metallic bond itself is simply that really strong electrostatic force of attraction between the positive metal ions and the floating sea of negative electrons. It acts like an incredibly strong glue holding the whole lattice together.
Moving right along to Section 2. Heat and electrical conductors. Let's see how that sea of electrons translates to conductivity.
So how exactly does electricity flow through, say, a solid copper wire? Follow the logic here, it's pretty brilliant. Because those electrons are already free-floating, a solid piece of metal can conduct electricity effortlessly. When you apply a voltage across the metal, those delocalized electrons suddenly experience a force. They just drift right towards the positive terminal, and that exact movement, that physical flow of electrical charge, is what creates an electric current.
This really highlights why metals are kind of in a league of their own. See, metals conduct electricity as solid objects precisely because those delocalized electrons are already free to move. But if you look at ionic compounds, like everyday table salt, they absolutely cannot conduct electricity as solids because their ions are locked tightly into a rigid lattice. You actually have to melt or dissolve an ionic compound just to free up its charge carriers. But metals, they're ready to conduct right out of the gate.
And boom! That actually solves our teaspoon mystery from earlier. When the bottom of the spoon gets heated by the hot tea, the delocalized electrons right there in that specific region instantly gain kinetic energy. Because they aren't tied down, these super fast-moving electrons travel rapidly up through the whole structure. As they zip around, they physically carry and transfer that kinetic heat energy to other electrons and ions right up the handle. Wood just doesn't have these free electrons, so the heat stays trapped at the bottom.
Which brings us to Section 3, bending without breaking. Let's talk about why metals are malleable. Notice how metal atoms naturally stack up in these incredibly neat, regular layers. If you take a hammer to a piece of metal, you're applying a massive force. But instead of just breaking, that force simply causes those atomic layers to smoothly slide right over one another.
So why doesn't it just snap in half? Well, in a metal, the bond is non-directional. That sea of electrons acts almost like a flexible glue that physically moves right alongside the sliding ions, maintaining that strong, attractive bond the whole time. But in an ionic crystal, if you force the layers to slide, you suddenly align positive charges directly next to other positive charges. That causes massive, instant repulsion, and the whole thing shatters. That's exactly why you can hammer a piece of gold into a paper-thin sheet, but an ionic salt crystal will just shatter into dust.
All right, Section 4, mixing it up with alloys. Time to upgrade some metals.
Now keep this in mind. An alloy is a mixture, not a chemical compound. That's a huge distinction. We're physically blending different elements together here without them chemically reacting to form a brand new molecule.
The whole goal of this mixing is pretty much always to create a material that's harder, stronger, or just way more resilient than the pure base metal on its own.
When we actually make an alloy, we're introducing a massive structural difference at the microscopic level. Think about the contrast here. A pure metal has those nice, uniform, easily slidable rows of identical atoms. But an alloy? It's totally disrupted. We intentionally scatter differently sized atoms of a completely new element straight into the mix.
So the real magic here is what we call the disruption effect. Because those neat layers are suddenly blocked by atoms of totally different sizes, they literally can't slide past one another smoothly anymore when a force is applied. By purposefully removing that slipping mechanism, the resulting alloy ends up being significantly harder and more rigid than the pure original metal. We've essentially jammed the gears on a microscopic level.
And finally, Section 5, a world of alloys. Let's see how we use this trick in the real world.
By just tweaking the recipe, we can engineer exactly what we need for modern life. Take aluminum. Mix it with some magnesium and manganese and you get bermabrite, which is perfect for tough Land Rover car bodies. Mix it with copper instead and you get duralumin, which is incredibly lightweight but strong enough for aircraft pistons. Pure gold is actually way too soft to wear, but 18-karat gold mixes in silver and copper so your jewelry doesn't just bend out of shape. And of course, mixing soft iron with just a little bit of carbon gives us steel, the absolute backbone of modern construction.
And just to give you an idea of how incredibly precise these recipes really are, imagine an alloy containing just 2 atoms of an element mixed in for every 25 atoms of a base metal. That tiny, almost microscopic addition yields exactly a 7.5% composition. Material scientists are calculating these hyper-specific percentages to engineer the exact perfect physical properties they need for a job.
So, just to wrap up this explainer today, we've seen how that invisible, totally free-flowing sea of delocalized electrons gives pure metals their crazy flexibility and their ability to conduct heat and electricity so perfectly. And we've also seen how we can cleverly hack that natural system, mixing in differently sized atoms to disrupt those sliding layers, locking them into place to build super rigid, incredibly strong alloys.
It honestly is kind of mind-blowing how much power we have to shape our physical world just by understanding what's going on at the microscopic level. So I'll leave you with this to ponder as you look at all the materials around you. With the entire periodic table at your disposal, what would you mix together next? What new superpower would you want to engineer? Thanks for hanging out with me for this explainer, and stay curious.